In this lecture, we're going to talk a little bit about the history of chemistry and how some fundamental chemical laws were formulated. This is a part of chapter one, and it's rare, really, in general chemistry that we give full acknowledgement of the history of science. We kind of tend to teach it in an anachronistic way, not focusing on the history of it. But this chapter is one of the rare instances where we give credit where credit is due in deriving some of the fundamental laws that underlie chemistry as we know it today. The first of those laws was formulated by the Frenchman Lavoisier in 1789, and it's the law of conservation of mass, or you can think about it as conservation of matter. And in its simple poetic formulation, this law states that matter can neither be, you can fill in these blanks, created nor destroyed. Matter can neither be created nor destroyed. It can just change forms, okay? It can undergo changes, be they physical changes like phase changes or chemical reactions, chemical changes that break bonds, reorganize atoms to create new molecules, for example. So matter can neither be created nor destroyed. It just changes forms. Lavoisier found this by weighing reactants and products of various reactions. And he found that the mass of what he started with, that's the reactants, that he used in chemical reactions, equaled the total mass of the products that were formed in the reactions. So by doing very careful quantification before and after chemical reactions, he was able to formulate this law that matter is neither created nor destroyed during these chemical changes. Shortly after Lavoisier in the early 1800s, another French scientist, Proust, defined the law of definite proportions. And the law of definite proportions really is just about ratios. And this is something that may seem obvious now, but it wasn't so obvious 220 years ago. A given compound always contains the same elements in the same ratios by mass. So water is always H2O, definite proportions, 2 atoms of hydrogen for every 1 atom of oxygen. Salt, NaCl, 1-to-1 ratio of sodium and chloride. And then shortly after Proust, it was an English school teacher named John Dalton who started. Dalton is responsible for atomic theory as we know it, but John Dalton uh, defined the law of multiple proportions, which is very interesting because two elements don't always make the same compound. Two elements can combine to form more than one different type of compound. For example, let's take carbon and oxygen. Carbon and oxygen can combine together to form carbon dioxide and carbon monoxide. And you probably have heard of carbon monoxide. It's very poisonous product of incomplete combustion. Okay, carbon monoxide. So that is very different from carbon dioxide, which is not toxic. Okay, it's an important part of our atmosphere. It is one of the major ingredients in photosynthesis. So carbon and oxygen can combine in a 1-to-1 ratio to make very toxic carbon monoxide, or a 2-to-1 ratio to make carbon dioxide. Okay, so we can have these two elements come together to form more than one different type of compound. Same goes for hydrogen and oxygen. Hydrogen and oxygen can form water if they combine together as H2O2, or they can combine together as H2O2 to make hydrogen peroxide. Hydrogen peroxide, of course, is very different from water, and hydrogen peroxide is a great disinfectant in nature. It's used as part of chemical defense systems. So it's an important antimicrobial compound. So hydrogen and oxygen can combine in these varying proportions. Oxygen Oxygen itself can make diatomic oxygen, which is the major ingredient in air, or triatomic oxygen, which is also known as ozone. Ozone is a really potent air pollutant. It's also the component of the ozone layer up in the stratosphere that protects us, shields us from the sun's harmful UV radiation. But these are very different gases. Okay, so oxygen, even just that one element can combine in multiple proportions. If nitrogen and oxygen come together, they can make a whole variety of different compounds, such as dinitrogen monoxide, uh, nitric oxide, nitrogen dioxide. This really shows the law of multiple proportions because you have varying ratios of nitrogen to oxygen, and these are all very different compounds. So the first one is nitrous oxide, and nitrous oxide, you may have heard of it. It's laughing gas used as a general anesthetic as at the dentist's office, for instance. Nitric oxide is a really potent air pollutant. It's a component of smog. At the same time, it's an important signaling molecule in the body. So, nitric oxide is really important in living systems for blood flow, for example. Nitrogen dioxide is another air pollutant. So, let's see. Nitric oxide is a signaling molecule. Nitrogen dioxide is a component of acid rain that is responsible for when it dissolves in raindrops, it basically forms nitric acid. So it can be very damaging in the natural ecosystems. Okay, so those are just three fundamental chemical laws.